So we know that malware is sneaky. It tries to hide. It tries to evade detection and to obfuscate its actions. And it turns out that most of what we know about these sneaky behaviors comes from observing the malware samples in lab environments. And in the next 20 minutes, I will tell you some of the lessons from the largest study of malware behavior in the wild, where we looked at how the behavior of individual samples changes from one host to the next in 1 week to another. Now, the main tool that we have today for understanding malware behavior is called dynamic malware analysis, which involves collecting and analyzing execution traces of these malware samples. And this is in contrast to static analysis, which involves analyzing the binaries. Now, dynamic malware analysis has many applications, such as creating rules and signatures for malware detection, clustering malware samples into families, anomaly detection, understanding new malicious behaviors and campaigns, attack attribution, and many more. And dynamic malware analysis is an experimental technique. So you probably see something like this. So detection rates that are pretty high, above 95%, for fairly low false positive rates. And if the situation is the same in research, where there are many research papers published on new ideas for detecting malware. Most of them, the evaluations report very high performance numbers to the point that they appear to leave very little room for improvement. So this would make it seem that malware detection is a solved problem. But unfortunately, when these tools are deployed in the real world, the performance is nowhere near to these numbers. So in fact, instead of reflecting a solved problem, these numbers provide a false sense of security. Now, we are fairly skeptical in this community. I bet that you can already think of a few reasons why this may be happening. So I just want to clarify that this talk is not about flaws in experimental evaluations, the base rate fallacy, malware evolution that leads to concept drift. Actually, for this one, stick around for the next talk, or misleading marketing claims. Right? Even in the absence of all these problems, the performance in the lab will not match the performance in the real world. And to understand why, let's take a closer look at how dynamic analysis is done today. So usually, most often actually, the behavioral traces are collected by executing the samples in a controlled environment called a sandbox. Usually based on virtual machines. And this is an environment that prevents the malware samples from causing damage or from propagating. However, we know that in the real world, the same malware sample may have different behaviors when it's executed on different hosts and at different times. And researchers have coined the term split personalities for this type of behavior. Now, this is not a new concept. Security professionals have known about split personalities for a while, but this became a problem that really came to the attention of the community. There's something serious that needs to be fixed with the discovery of red pills, which malware can use to detect that it's running inside of a virtual machine and therefore to evade detection and analysis. Now, the first red pill dates from 2004, but many more have been discovered since then. And the research in response to this has followed mainly two directions. The first one is program analysis techniques to detect split personalities in sandboxes. And these mainly focused on time-based triggers and sandbox evasion. And on the other hand, the other direction was towards developing better sandboxes by bringing them closer to bare metal, or by adding aging artifacts, or by randomizing the VMs. So because all this past work focused on what malware does in a sandbox, we asked ourselves, what else could we learn about split personalities but by analyzing traces from the wild? And to begin answering this question, let's take a look at some of the answers that the previous research did not answer. So first of all is, how do malware behaviors vary in the wild? So how much variability there is between executions, what parts of the behavior vary the most, how does this impact malware dynamic analysis? Perhaps it doesn't impact that much, so we shouldn't worry about it. And finally, what can we do about it? So now, to put this on more concrete terms, let's take a look at an example. So here on this slide, you have a portion of the pseudocode for the Ramnit worm. And one of the things that this worm does is that it tries to exploit a certain vulnerability. This is on line 22 here, with the aim of achieving privilege escalation. Now, when this happens, when the exploit executes, this results in the creation of hundreds of Windows mutexes until the exploit succeeds. However, this only happens on Windows 7, on hosts that have not been patched, and when the worm is run in non-admin mode. So who cares? Well, if you are an engineer developing malware detection signatures, and you base your signature on the trace that includes these hundreds of mutexes, this signature may be ineffective on hosts where that have been patched, or where the worm is running in admin mode. Now, if you are a user of such tools that include signatures based on these types of signatures, you may not know the true effectiveness of the tool, because this will depend on how prevalent this trace is in the wild. If it accounts for 1% or for 99% of the traces in the wild, you will see very different results. And what's worse, even the vendor will be unable to estimate the effectiveness without collecting traces in the wild. And then malware analysts are facing this problem of determining which part of the traces that they're analyzing are representative of the malware's behavior. In this case, the trace that contains all the string of mutex creations is not representative. So now the reason why we don't know these things is because it's hard. We need executions from the wild, execution traces collected from real-world hosts. Right? And it turns out that some security companies are already collecting such data. So we partnered with one of these companies to conduct a large empirical study of split personalities in the wild. So we collected 7.6 million execution traces coming from over 5 million real users' machines. This map shows the geographic distribution. And importantly, this includes multiple traces per sample. Now, this data, these execution traces represent real-world infections, because we do not distribute any samples to these hosts, we do not provide inputs, and we do not trigger the executions, and the antivirus will block all known malware. The executions are collected not for the purposes of our study, but as a last line of defense. And they're only collected when the antivirus cannot classify a sample as either benign or malicious. And as soon as the sample does something that the AV will recognize as being malicious, the execution is terminated. Finally, no private user data is collected here. So the first finding that I want to tell you about is that benign programs also have variable behavior. So if you look at a typical benign sample, and you look at the difference between the longest 25% traces and the shortest 25% traces, this difference is 8 or more actions. Now, potentially unwanted programs have more variability. In this case, the difference is 19 actions. But malware samples have a lot more variability. Here, the difference is going to be 59 actions. So now, the word clouds on this slide illustrate the relative amount of variability for different types of actions. Note that file creations are the type of actions that vary the most for all categories of software. And this is true both in terms of the number of actions as well as the parameters, so the different file names that are created. Especially malware tends to create a lot of unique and random file names. So now there are many reasons for these behavioral differences. There are, of course, malware implements evasive techniques, but there are also differences in operating systems and libraries, like we've seen in the Ramnet example. Malware may attempt some risky operations that fail on some hosts. Malware may receive different commands from its command and control channel. We've also seen differences between the first execution and the second execution of the sample on the same host, and that's because the initial installation performs some one-time operations, random file names, and many others. So now, most of the research has focused on addressing sandbox evasion, which is the first bullet here. But as you see, there are many other reasons for behavioral variability. So even sandbox traces cannot account for the range of behaviors that are encountered in the wild, and that's even if you always catch sandbox evasion. Now, there are a lot more results in our paper. I encourage you to read it if you're interested. I want to spend the rest of this talk focusing on what these results mean for you. So if the problem of split personalities affects your job, then what can you do about it? So I expect that most of you here do not work on malware analysis directly, but you may need to use tools such as malware detection or malware classification to protect your organization. So in this case, my advice is trust but verify. And to illustrate this, we conducted an experiment with a malware clustering technique with the aim of understanding the impact of this behavior variability on malware clustering. Now, clustering is an unsupervised machine learning technique, and the goal here is to identify which samples are similar enough that they likely belong to the same family. So usually the way this is done is a bunch of traces for different samples are provided to the clustering tool, and the different clusters are produced that indicate different families of malware. Now, all the papers that I've read on this topic used only one trace per sample. So we decided to use 4 traces per sample just because we could. If clustering is really able to separate the malware families, then we would expect to see something like this. We would expect to see that all the traces of a sample would be placed in the same cluster. But actually what we see is this. 1/3 of the samples we experimented with exhibit sufficient variability that their traces are placed in more than one cluster, with 1% of samples, each trace being placed in a separate cluster. And note that we only observed this because we used 4 traces per sample. So this suggests that whenever you're doing clustering experiments with only 1 trace per sample, the resulting accuracy will be overestimated. And what's even worse, even independent evaluators and researchers and the vendors themselves will not be able to tell you how large the overestimation is without using traces in the wild. So for this reason, my advice is trust but verify. Evaluate the tool rigorously in your environment, because even with the most rigorous evaluations, the results may still not reflect what you are going to see in the future. Now, if you are somebody who develops rules for detecting malware, my advice is to use traces from multiple executions in the wild. So here I'm going to tell you about another experiment where we looked at the impact of variability on malware detection. And in this experiment, we focused on WannaCry, the famous worm and ransomware. We We trained several supervised machine learning models to detect WannaCry. And in this case, we also collected contemporaneous sandbox traces. So these traces were actually executed by 2 different sandboxes at the time, around the time when we were doing the data collection in the wild. And we looked at 2 sandbox traces, two separate sandboxes, because some of the best practices recommend combining sandbox traces in order to account for behavior variability. So the results that I'm presenting here are in terms of the true positive rate, so the detection rate for 1% false positives. So when we train our models on Cuckoo Sandbox and we test on Cuckoo Sandbox, we get 76% true positives. When we train on Cuckoo Sandbox and test on Hubble Sandbox, we have a little bit of a performance drop. But when we train on Cuckoo Sandbox and test on the wild, we have a huge performance drop. 18% true positives is basically useless. So therefore, we combined, as recommended, we combined the sandbox traces, and we trained on the combined sandbox traces and tested in the wild, and we got a little bit of improvement, but not much. So to understand why this happens, we try to visualize the feature space that these classifiers are operating on. And so our features are counts of token extracted from WannaCry parameters. And so this is a high dimensional space, so we use the projection into 2 dimensions to visualize it here. This means that the 2 axes, the x and y axis on this plot, are not meaningful. The numbers on the axis are not meaningful, but the relative distances between the points are. So we can see here, this plot here only shows the 2 sandboxes. We can see that the traces in the sandbox are pretty well clustered together. But then when we look at what happens in the wild, we see a lot more variability. And in fact, if we try to identify where the sandbox traces are on this second plot, they are right here in this very small area. And this is because sandboxes do not account for the broad range of behaviors in the wild. It seems that models based on one sandbox tend to generalize well to another sandbox, but very poorly to behaviors observed in the wild. So for this reason, my advice is to use multiple traces from executions in the wild to create these rules. Now, you may be wondering, okay, just how many different environments? And it seems that 3 is a pretty good number. After 3, we observe diminishing returns. And this is actually good news, because it suggests that there isn't an infinite number of environments where the behavior will differ. After observing a few number the sample in a few number of environments, we can get a good coverage of its behavior. Now, behaviors also vary over time. Here, you want to collect executions 3 to 4 weeks apart. However, here, this seems to be less useful than executing the sample on multiple machines in terms of improving the coverage. So now, summarizing the current practices, malware analysis tools are in demand. There is a 5 billion malware analysis market expected to grow over the next decade, and today it relies heavily on sandbox collected traces. And this introduces a number of blind spots. We tend to overlook environment and time-dependent behavior, especially when we're using only one trace per sample. We observe a narrow range of behaviors compared to what's happening in the wild, even assuming that you have the perfect solution against sandbox evasion. Well, it's hard to determine which actions or parameters are representative of the malware's behavior, and this ultimately ends up in an overestimation of the accuracy of clustering and detection. So before I conclude, I want to thank my collaborators. First of all, my student, Erin Avlazagai, who was the lead author of this study, my student, John Kaya, and my former student currently, Dr. Zhu, as well as my collaborators, Leila Bilge and Davide Balzarotti. This project is a great example of industry-academia collaboration, with thought-provoking findings and actionable implications. And generally, there is a lot of great science coming out of such collaborations. I think we've heard another couple of examples today here at Enigma. These collaborations will have a transformative effect on the next generation of security products and services. So I invite you all to check them out, and perhaps you will even find opportunities to participate in these collaborations. So now I want to leave you with two thoughts. The first one is that malware analysis should be based on multiple executions from the wild, that this can be done ethically, and there are security companies today who are in a position to do it. And the second one is that this is a radical shift in the way, from the way that dynamic analysis is done today, but it's a shift that can bring unique new insights. And if you're looking for the next big thing in dynamic malware analysis, this may be it. Thank you.